Okay, in this segment we're going to actually start talking about basic static memory. These are circuits that will allow us to store one bit of information. The simplest of these types of circuits is something called a bistable element. And this bistable element has two stable states. That's why it's called bistable. And the circuit is very simple in terms of logic schematic symbols. It looks like a pair of CMOS inverters arranged in a ring like this. Chasing their tail, so to speak. In terms of transistors, you would have two CMOS inverters. Like so. And they would be connected so that the output of this one goes to the input of this one, and the input of this one goes to the output of that one. And these two outputs we're going to call Q and Q bar. Obviously, one here is on the output of an inverter and the other is on the input of an inverter, and that being the case, they should be complements of each other. And so to be consistent here, we'll call this one Q and this one here Q bar. And we want to think about how this element works. So let's first of all consider the two possible stable states of this so-called bistable element. We're going to assume, for the sake of argument, that Q is equal to 0 and Q bar is equal to 1, and think about whether or not that's a stable state and how the circuit works at the transistor level. So that would correspond to having Q be 0 volts and Q bar correspond to VDD. And we want to think about, is this state of the circuit self-consistent? Well, let's think about what happens when we have Q at 0. Well, that's going to be the gate voltage of this PMOS transistor. So this PMOS transistor is going to be on, and this NMOS transistor is going to be off. Right, so we're turning off the NMOS transistor and turning on the PMOS transistor. And with the PMOS transistor turned on and the NMOS transistor turned off, the NMOS is let go of Q bar and the PMOS is strongly driving it to VDD. And so here, this output being at VDD is consistent with that. Now if Q bar is at VDD, that in turn comes back around here and turns this NMOS transistor on and turns this PMOS transistor off. And so here we have this PMOS transistor having let go of Q and this NMOS transistor down here strongly driving Q to 0. And so this is a stable configuration, or a self-consistent configuration at least, as we chase this around the feedback loop here. If we think about perturbing this somewhat, like let's say somebody came in here and made this, instead of 0 volts, made it 1 volt. Well, what would that do? Well, that would kind of turn off the PMOS transistor here a little bit, but it would still be on with something like 4 volts of source to gate voltage. We would have turned this partially on, but it's not on very strongly. It's just a little bit above threshold. And so this thing is blasting out, let's say, hundreds of microamps of current, and this thing is maybe capable of sinking 20 microamps of current or something of that nature with a volt on the gate or so. And so still, this inverter is going to be strongly pulling Q bar up to VDD, and that's going to have the resulting that results in this transistor still being off and this one being on. And so very quickly, the current that this transistor is now pulling down with, because this is now putting this NMOS transistor into saturation, so this is pulling an actual current against this 1 volt here. It's going to pull this back down, and it's going to restore this to 0 volts. And that's going to make this transistor go back to fully off in a very short amount of time. Likewise, we could imagine perturbing this down from VDD, and that would partially turn this transistor off and partially turn this transistor on, but it would still be balanced so that this would be probably still quite close to 0, and that would in turn maintain this transistor pulling up against this perturbation from VDD and restore the state back to this configuration, which means that this is a stable configuration for these voltages to be in. Okay, so let's consider a second possibility, and that's putting Q at 1, and Q bar would therefore be at 0. And so that means that Q is at VDD, and Q bar would be at 0. Let's think about the state of these transistors here. So with Q at VDD, that means that this transistor is going to be off, this transistor is going to be on, strongly pulling Q bar down to ground. So that's consistent with Q bar being at ground. That in turn makes this transistor off and this transistor on strongly. And that's going to be consistent with Q bar being pulled up to VDD, or the Q being pulled up to VDD. And so this is also a self-consistent state, a stable state for this element to be in. So these are the two stable states, and we basically use one of these two configurations to represent a digital 0, and one of them to represent a digital 1. And Q is typically considered to be the memory it's stored there. So Q being 0 would be storing a 0, and Q being 1 would be storing a 1 in this. Now it turns out there's a third state, which is technically something called a stationary point of the circuit. And this is something of an idealization, but we might call this the one-half state. Just down here, 1/2. And what this is, this would be Vm. V sub m is the transition threshold for these inverters. V sub m. So remember, V sub m from our last segment where we talked about the voltage transfer characteristic, that is the voltage at which the inverter's input is equal to its output. So with Q at Vm, that means that this inverter here would have its output at Vm, and that's the input for this inverter, so that means that this inverter is at its transition threshold and its output's at its transition threshold. So that's consistent with what we know about the voltage transfer characteristic of these inverters. The question, though, is this a stable state? So if we perturb it, what happens? Let's suppose that we make this we increase this node from VM? Well, that's going to turn this transistor up a little bit. So let's suppose we increase above VM. So it's going to turn this current up and this current down. It's going to decrease IP, it's going to increase I sub n, and that in turn is going to make this less than V sub m. And that's going to turn the current in this transistor up, and it's going to turn the current in this transistor down from what it was. And that's going to have the effect of pulling this node further up, right? So that we're decreasing the amount by which the NMOS transistor is pulling down and increasing the amount by which the PMOS transistor is pulling up. That means that this voltage is going to go further up. It's going to actually accelerate up. And this one is going to accelerate down. And so this, if we perturb this away from VM in the upward direction, that's going to have a tendency to send Q to the positive rail and Q bar to the negative rail. Okay, so this state is a stationary point of the circuit, meaning that if it's balanced there, it will theoretically stay there. But any little tiny perturbation of that state is going to result in the system falling into either the 0, 1 or the 1, 0 state, depending on which direction that perturbation was in. This is kind of like the inverted pendulum, right? So the pendulum has a stable state where the pendulum is hanging straight down. Right, so if we have a pendulum, there's a stable state where the pendulum is hanging straight down, right? But there's also a state up here where the pendulum is inverted. And if you perturb it this way the slightest bit, it's going to fall this way. If you perturb it slightly this way, it's going to fall this way. And that's exactly what this 1/2 state is like. It's called a metastable state. These are both stable. So these two stable states have this metastable state in between them. And the basins of attraction for these stable states go right up to that metastable state. And that metastable state is the boundary between those two states. Okay? So we're not going to talk about metastability. It's actually a potential issue in the design of reliable digital systems. But the biggest issue there, just summarizing, would be that theoretically this metastable state can take an unbounded length of time to resolve itself into one of the two stable states. And so that's bad news if you have a clock that's ticking at a certain time by which all things need to have stabilized. And so eliminating metastability is a key issue in synchronous digital systems. But we're not going to talk at length about that. You can look up the metastability problem for digital systems if you want to know more about it. So this is the simplest memory element. The problem is that we don't have any way of setting the state. If the state is, starts out 0, 1, then it's in a 0 state, and if it starts out at 1, 0, it's in the 1 state. But how do we actually get the circuit in that state to begin with? Well, we can add some extra access devices. So if we, for instance, wanted to, we could put an extra NMOS transistor here and an extra NMOS transistor here. And we could call this input here S. We could call this input here R. And this circuit now becomes what's called an SR latch. And in this case, if we assert S, if S goes, let's see, how do we do this? So S and R, and then we'll say Q, and Q bar. So there's 4 possibilities for S and R. So if S and R are both 0, then Q and Q bar just maintain their state. It's like these 2 transistors aren't there, and whatever state the bistable element happens to be in, that's just maintained. And then if we assert, let's take this third row here where we assert S. So if S is 1, that pulls down on Q bar, making Q bar equal to 0. And through this inverter over here on the right, that sets Q to 1. And so S is set. That stands for set. So we set Q to 1. If we take the, sorry, that's the wrong row of the truth table. 1, 0. If we assert R, we make R go high, then that's going to pull down on Q. And through this feedback inverter here, that sets Q bar to 1. And so that's said to be reset. So that basically sets Q low. And so these are called access devices. And these allow us to set the state of the bistable element. And that makes this bistable element into an SR latch. This is a so-called SR latch. A set-reset latch. Now if we assert S and R at the same time, then we're pulling down both on Q and Q bar, and that's not a happy thing to do. That actually will set this latch up into its metastable state and could possibly avoided, because when we let that state go, what will happen is basically unpredictable. So this basically puts the latch into the metastable state. And the result is unpredictable. So if you want to implement something like a coin flip, that's usually how people think of this. This may not be a bad way to do it. But for the purposes of making a reliable digital memory element, we typically try to avoid this particular state. One of the things that we didn't talk about here, though, is something called the writability problem. Right, because what we're doing here with these 2 access devices is we're attempting to overpower or overwrite the memory that's stored in the latch at the moment. Like, for instance, let's suppose that Q is equal to 0 and Q bar is equal to 1. Okay, and we're trying to set the latch into the opposite state, the 1, 0 state. Well, this transistor is on and this transistor is off. Okay, so the PMOS transistor here is on, and when we assert S, we set S to high, we'll have this transistor on here, and so we have this PMOS transistor on fighting against this access device, which is also on. And if this NMOS transistor is not strong enough to overcome this PMOS transistor and get this feed-forward inverter to get beyond or below its transition threshold so that this gets above V sub m, then we're not able to overwrite the state that's written in here. And so when we deassert S, we make S go back to 0. The fact that this transistor is on, so we need to get the voltage here on Q to get larger than V sub m in order to terminate this fight. And that puts a sizing constraint on these two transistors so that the NMOS access device must be strong enough to overcome the PMOS pull-ups. In the bistable element. If not, we can't write a new value into the latch. That's the writability problem. And so this particular implementation of the SR latch is not immune to that sort of problem. We can make it immune to that sort of problem. So an SR latch So let's start with our SR latch here. So here's our pair of inverters. And they are cross-coupled in the same way. So this is Q, and this is Q bar. And we have our S input here, and we have our R input over here. You'll notice that if we think about each half of this circuit as a gate, as a CMOS gate, these are identical gates, right? We've got two transistors in parallel with each other in the pull down, but we only have a single transistor in the pull up. Right, so here we have these two transistors in parallel in the pull down and these two transistors in parallel in the pull down, and we have a single transistor in the pull up. So the thing that we're missing from the pull-up network here is a PMOS transistor who has the S input, and the thing we're missing here is a PMOS transistor that has its gate connected to the R input. And so, if we like, we could imagine synthesizing an appropriate pull-up network for this pull-down network to incorporate that extra transistor into the structure. So suppose we do that. So we have here two transistors in parallel in the pull down, and so we would want two transistors in series in the pull up. And so what we can do is we can basically just add a PMOS transistor here, gated by S, and a corresponding PMOS transistor here in series, gated by R. And so normally, let's say when S and R are both low, these are on and these are off. But let's suppose we want to set the latch into the 1 0 state. Let's assume it's at 0 1, and so this would be on and this would be off. This would be off and this would be on. Well, if we then assert S, right, this transistor will cut off the pull-up network. Right? So this pull-up network, which has this PMOS transistor that's connected to Q, is still on, but this access device that we've added here actually cuts off this pull-up and terminates that fight, or prevents that fight from even happening. So this gets pulled down to 0 unopposed, and that will force the state of Q to become a 1. And then when this goes away, this is now off. This is now on. We basically have successfully flipped the state so that this is now I'm sorry, this is on and this is off, and so this would be set to 0 or maintained at 0 by the state of the two transistors in the feedback here. And so this is a latch. It's obviously slightly more complicated by the addition of these two extra transistors over this version, which has the writability problem. But this is now something that we can draw in the following way. We have two, these are actually NOR gates. If you look back and see how we implemented NOR gates, these are two NOR gates. And this is the way it would typically be drawn in a logic schematic, where we have the two, what were the two inverters, become two cross-coupled NOR gates. And this would be, let's say, Q and Q bar. And the Q input is R, and the Q bar input is S. And so this is basically the logic schematic of this transistor level schematic here. And so this would be a very nice way of implementing an SR latch without the writability problem issues of this. However, this comes at the cost of having two extra transistors. And sometimes when you're building these kinds of memory elements, like for instance in the context of a static RAM, where you want to have as many of these circuits that could store a bit of information packed in a given area as possible, having those extra two transistors in there is something you don't necessarily want to do. And so you wind up doing things that you like putting up with having to size these transistors appropriately, and worrying about that writability problem in this for the sake of getting the density up. Okay, so that's just a brief introduction to storing digital memory. In the next segment, we'll continue on with this discussion of digital memories, and we'll talk about some state holding gates, and then that'll probably be about it for our foray into transistor level CMOS digital design. So we'll see you next time.